Alright, so in today's lesson, we're going to be talking about kinetic energy. However, first we're going to review over what we've talked about so far in this unit. Alright, we have a concept called work, and that's the ability of something, or energy is the ability of something to do work in physics, and then we define that with an equation, which is force times distance, and then if there's an angle of any kind, we do cosine of theta, only if there's an angle. If it's something against gravity, we use this equation, mgh, that's mass times gravity, which gravity is always 9.8, acceleration due to gravity, and then height, which we've measured in meters. Now, if something's if you were given not a mass, if you were given, say, a weight, then this equation would be, since m times g is weight, it'd be, that's the same as force of gravity times height. So either forms of those could be in there. If I was given, say, 15 kilograms, I'd want to plug that in for my mass and use this equation right here, the m times g times h. If I was given, say, 20 newtons, I could plug that in for my f of g and do Fg times height to figure out work. That's if it's against gravity. All right, that leads us into our talking about potential energy. And we said potential energy is the same equation, m times g times h. Mass times gravity, which is 9.8, and then times height, and it could also be the same thing, f of g, that's weight, times height. Can also be used, just depends on if you're given a mass or if you're given a weight in the beginning. You could always be given a weight like 20 newtons, and then, if you were to plug it into mgh, you'd have to divide it by 9.8 to get your mass in kilograms, but then you'd just be multiplying by 9.8 again once you plugged in your g here. So really, just start off using that one if you're given newtons. And then that leads us to kinetic energy. So kinetic energy, like all this work and energy values, they are scalar, meaning they have magnitude but no direction, and it's measured in the units is joules. So the units for work, energy, and both types of energy, potential and kinetic, is going to be joules. And our equation for that is, we can use Ke for kinetic energy, and it's 1/2 mv squared. That's the equation. So we could write it like this: E subscript K, that's kinetic energy, equals 1/2 mv squared. Either one of those forms you want to use. Now, m is going to be my mass in kilograms, and v is going to be the velocity, or really just the speed. It's really not the velocity in this case because it's a overall kinetic energy is a scalar quantity, so that would be my speed in meters per second. So if I look at this first example problem, a 60.0 kilogram student is running at a uniform speed of 5.70 meters per second. So what am I given in the problem? I'm given a mass, and I'm given a velocity of v right there. So I'm going to start from my equation, and I'm asking for what is the kinetic energy. So kinetic energy is equal to 1/2 times mass times velocity squared. So now plug that in. Kinetic energy equals 1/2 times my mass, which is 60.0, times my velocity squared, which is 5.0 squared. So I'm going to plug that into my calculator. So take 5.7, square that. I'm going to multiply it by 60. And I'm going to divide by 2, for the 1/2 of that, and that equals 974.7 joules. So next, have the kinetic energy of a 2.1 kilogram raw tomato is 1.00 times 10 to the third joules. Now that's the same as saying 1,000 joules. That's like 10 to the third, be moving your decimal over 3 places. But it's giving me a mass in kilograms, and it's giving me a kinetic energy, and it's asking me how fast it's moving. So my equation again is kinetic energy is equal to 1/2 mv squared So my kinetic energy, like I said, was 1,000. That's just in scientific notation. Equals 1/2 times 2.1 times velocity squared. So that would equal 1,000 equals 1.05 times v squared. So I'm going to divide both sides by 1.05. And then that's going to be v squared is going to equal 1,000 divided by 1.05 gives me 952.38. And then to get rid of the square, I need to square root both sides. And my velocity is going to equal 30.9 if I go to one decimal place. And velocity is in meters per square. And that's really the basic two types of problems that you'll have with this kinetic energy equation. The only other thing you have to solve for is mass, which is, the same thing. You just plug it in for your numbers and then do an algebra to solve for your unknown. Now, one other part of this is the work energy theorem. And if that says if the net force acts on the object, it must be accelerating. And this must be proportional, and I should say to its change in kinetic energy. So our equation says that the change in kinetic energy, that's what that triangle means, is equal to your net force times your distance. So pretty much change in kinetic energy is equal to F net times D, which is work. So that's just like saying that the change of energy, or kinetic energy, is equal to work. So if we look at this problem right here, the sprayer exerts a net force of 260 newtons, so it's telling me a net force over a distance of 35 kilometers. What is this change in kinetic energy? Well, this equation tells me that the change in kinetic energy is equal to F net times D. So if you see that change in kinetic energy, you need to know, you need to use this equation right here. And I'm actually solving for the change in kinetic energy, this whole left side here. So the change in kinetic energy is equal to F net, which in this case is 260, times my distance, which is 35. And you get 9,100 and joules would be the units for the answer. Now this last problem we're going to omit. We're not going to go over it. So you can just exit out. There won't be any examples like that. All of our examples actually will probably be like these first two types of problems, where in this first one you're solving for the kinetic energy, it's used to 1/2 mv squared. Units are joules for kinetic energy. Or you'll usually be asked for solve for how fast something's moving if you're given the kinetic energy and a mass, and then you plug it in, like I said, into your algebra. Don't forget to take the square root at the end when you get v squared is equal to whatever. You got to take a square root of both sides to find what your velocity or speed would be.